give this problem a read on your own. Pause it if you have to. So since 2000, the film cameras sold has decreased, meaning the rate of change is going to be subtraction. So that's for film. And that makes sense because, obviously, there's been an increase in digital things since 2000. At an average rate of 2.5 million per year. So that's your rate of change. Or more simply, your slope. At the same time, the number of digital cameras sold has increased at an average rate of 2.6 million per year. Same deal there, that's going to be the slope. Use the table to estimate the year in which the sales of digital cameras equaled the sales of film cameras. Now before we get too deep in this, if you're thrown off by this, just remember that if this is 2000, this will be your starting point. So that if we use X to represent the years, and X is 20, that would mean that this would be the year 2020. So let's define some variables. What will X be? What will Y be? For X, that makes sense to be the input of years since 2000, and then Y is going to be the number of cameras. So we're going to set up two equations, the first being the film, and then the second being the digital equation. And the whole deal here as you do this, we are dealing with the section where it says applying these concepts. So you're still kind of in the back of your head saying, well, is this going to be best on a graph, using substitution, or using elimination? So for the very first equation, you're thinking, well, if I deal with film cameras, the beginning point is that there's 20 million sold. And I'm pulling that from the table. And the film cameras are decreasing every year at a rate of negative 2.5 million. And so if I set up the other equation, this one is growing at a rate of 2.6 million per year with a starting point of 4.7. So this is starting smaller but growing, while this is starting larger but decreasing. And so as you look at this, you're like, oh, okay, it kind of stacks up nicely. Maybe I can use elimination. But I think that substitution is going to be best because the y's are already solved by themselves, which means you can just set the first equal to the second. And then solve it. And since solving is a little bit routine, I'm going to pause after this so that you can finish this on your own. My work will be up in 2 seconds. I'll scroll down so that everything's in the same window. Just using the whole deal to solve this, there you go. And there's no reason for you to plug this in, but I did just so that we could see that after 3 years, both sales would be 12.5 million. You can always do a check like that because it's a good thing to see, well, this would be going down, and the other would be going up, so they'd meet somewhere. But since they only really want to know the year, that would be enough. But it's better to be thorough. And speaking of being thorough, let me go back to what we're talking about here. We're solving real-world problems in an applied section of systems of equations, graphing, substitution, and elimination. This one lent itself really nicely to substitution, because you could just took one equation and set it equal to the other. And when you look at this, obviously, coming up with the most challenging thing in this is the equation. If you come up with those, solving isn't too bad other than the fact that this one has decimals. After this video, we'll do another real-world problem, but I'll save that for a second video. This is part 2 of 3.